Welcome to the second part of the optical properties of Martian dust. So I'm going to be focusing on the modeling part. So I'm Julia Martikainen and I work at the IAA. So I have a little bit of background about myself first. So I did my PhD in astrophysics at the University of Helsinki. I defended my thesis in 2021, so I am an early career scientist. My specialization is in light scattering, so the focus is in modeling. I have been also doing some experimental stuff like the measurements with the University of Helsinki spectrophotometer. Also now at the IAA we have the nephelometer that I have been using. And I did a lot of observational astronomy because I worked as support astronomer at the Nordic Optical Telescope on La Palma when I was doing my PhD. And now after getting my PhD, I started in the roadmap project as a scientist, and my focus is to retrieve optical properties for Martian dust. And I also do some astrophotography in my free time. So here's a nice image of a lunar eclipse on La Palma. So you can see the Milky Way core and the moon in the same picture. Okay, so this is the outline of my talk. So I will first focus on the theory, so just give some brief introduction, some background on the scattering theory, and then I will be going on the modeling part, so I will talk about what I have been doing during the project. So, as Olga already gave an introduction, roadmap, it comes from words role and impact of dust and clouds in the Martian atmosphere. So the aim is to use laboratory measurements and advanced models to better describe Martian dust and clouds. My aim is to retrieve scattering properties for Martian dust. And in order for me to do that, the first thing I have to do is to retrieve optical constants, because they are needed in light scattering and radiative transfer models. Now, what are the refractive indices, the optical constants? It can be divided into the real part, n, which describes the ratio of the speed of light in a vacuum to the phase velocity of light in the material, and to the imaginary part, k, which describes absorption of light inside the material. Now, the current optical constants for Martian dust, they have been retrieved from observations. Now, this sets limitations since there are multiple free parameters. Usually, simplified particle shapes are used. This can be spheres or spheroids or cylinders. And there are usually no direct particle size distribution measurements at the time of the observation. So we don't actually know what particle sizes we are looking at during the observations. So in order for us to characterize the samples well, we need experimental data. So this sets constraints on particle sizes and shapes, since the only free parameter really is the complex refractive index. And then we can use an advanced model to retrieve the scattering properties. Okay, so first just the basic concept. So what we are using in astronomy usually, what we are measuring. So photometry, this measures the intensity of the object's electromagnetic radiation. We are looking at also polarimetry. So it's the study of polarization of light, and spectroscopy. So it tells how much electromagnetic radiation is scattered, absorbed, or emitted by the object at different wavelengths. And in this case, we are looking at the wavelength range of 200 to 2000 nanometers, as this is limited by our instrument. So we can only measure reflectance spectrum at that wavelength range. So this is our wavelength range we have to look at. So this is from the UV to near infrared. Okay, so a little bit about the spectra that we are looking at. So we are looking at diffuse reflectance spectrum. So in other words, here's the surface and there's light coming and it's scattered by the surface. So if we have a mirror-like surface, very smooth surface, we see specular reflection. Now, specular reflection has the same angle between the surface normal as the incident light and the surface normal. However, when we are looking at a rough surface, the light is scattered to all directions, and this is called diffuse reflection. Now here on the right side, we have different reflectance spectra. So this is how the spectra usually look like. Here is just different paper sheets that have different colors. So here with the spectra, you can really see, for example, different colors. So we have a blue paper sheet, so you can see there's more reflection in the blue light than the red, so there's a slope here. And then on the other hand, if you're looking at a red sample, you see more reflection in the in the in the red than in the blue, and there's a slope towards the red. And this is depending on the composition of the sample. Now let's go to more in the scattering theory. So we have here, for example, a cloud of particles, and we have a light coming. Usually this is starlight, so we can look at the sunlight or any other star, and it hits the cloud of particles. It can be either scattered or absorbed. And then we see the scattered light here. And so the incident light can be characterized with Stokes parameters, I, Q, U, V, as Olga already explained to you before. And then this is the scattering matrix. So it describes the change in the state of the light when the light hits the cloud of particles. Okay, so let's look a little bit zoom in. So let's look at one particle. So as I said, that the scattering event can change the state of the incident light. So this is described with the scattering matrix. And the scattering matrix is a function of the scattering angle, or depending, some astronomers like to use phase angle. So this is just 180 degrees minus the scattering angle. So after a light beam, it interacts with an object. Part of it can either scatter or be absorbed. And there are multiple factors that affect the amount of scattering and absorption. So what is really important is the particle size and shape, optical properties such as the refractive indices, porosity, particle orientation, and the wavelength of the incident light. Okay, so now let's look a bit closer to the scattering matrix. So here we have again the Stokes parameters. So the I is the intensity of the light, then Q and U, they describe the linear polarization of the light, and then we have the circular polarization, which is the V. And this is the observed light, and this is the incident light. And then we have the scattering matrix. So what part scattering matrix elements are usually important that we are looking at is the F11 element, which is the phase function. So it's basically the intensity of the light as a function of a scattering angle. And then we are also looking at the F12 element, which is the degree of linear polarization when you are dividing it by F11 minus F12 divided by F11. And then further, you can look at, for example, the F22 element, and you can get the depolarization ratio, which is usually measured in LiDAR. Okay, so this is also something that Olga showed before. So the physical size of an object can be defined using a size parameter. So this is just the size of the particle divided by the wavelength. And these are the different regions. So Rayleigh is when the particle is much smaller than the wavelength. Resonance mean when the particles are on the size of the wavelength. And then the geometric optics where the particles are much larger than the wavelength. And I'll be mostly focusing on the geometric optics part. So I'm gonna talk a little bit more about geometric optics. When you have particles that are much larger than the wavelength, you can solve the scattering problem with the help of ray optics. So basically, we are using this phase matrix. So it's just another way to describe the scattering matrix. So, but we are using the scattering cross section. So it's the scattering matrix divided by the scattering cross section, and then these are constants. And the scattering cross section, now this can be divided into ray tracing part and diffraction part. Now it's really important because we are mostly, when we are modeling a surface, we are looking at backscattered light. So we don't need the diffraction part because this is only prominent in the forward scattering. So we can just omit it completely from the model. So what we are really looking at is the ray tracing part. And well, here is a sketch of what is happening in the model. So we have an incident ray going inside an absorbing particle. It can either be reflected or refracted inside the particle. And the ray, it will travel inside the particle and hit the surface. It can either be refracted out or reflected back in. And of course, because there is absorption, the intensity goes down. And we have some kind of a cutoff intensity when the value goes to 0. And that's when the code stops tracing the light beam. And of course, then the single scattering output, yeah, it's the scattering cross-section divided by the extinction cross-section. Okay, just I wanted to make clear the difference between single scattering and multiple scattering. So single scattering is when you have particles that are far away from each other. So when you look at one light ray, you only see scattering by one particle. And then the whole field can be obtained by just summing up the single fields. When you have multiple scattering, the light interacts with many particles before you are detecting the light. So you have to use radiative transfer equation to solve it. Okay, so let's go to the modeling part now that the theory was explained. So just to give you a general idea of what I have been doing, so the first part was to retrieve the optical constants, the refractive indices. So we are using advanced numerical methods in the geometric optics region and the measured reflectance spectrum of Martian dust analog samples, and also the measured size distribution of the analog samples. And for this, we needed narrow size distributions because we had to have the particle sizes in the geometric optics region, not smaller than that. So I want to make very clear that the refractive index, this is a material parameter. It is not dependent on particle shape or particle size. However, when we are retrieving refractive indices from, for example, measured reflectance spectrum, now reflectance spectrum is dependent on both the refractive index, the particle shape, and particle size. So for example, here we have a nice picture from Lucy et al., quite old, but they have done reflectance measurements of clinopyroxene, which has different particle sizes, so the refractive index doesn't change, the composition doesn't change, only the particle size. And you can see well, there's no text here, but basically the highest one has the smallest particle sizes, and the lowest reflectance is for the larger particles. However, the spectral features do not change, only the absolute level. So it is very important to use accurate particle sizes and shapes to retrieve the refractive index from the spectrum. Otherwise, you will be retrieving it wrong. However, when you have retrieved the refractive index correctly, you can use it with any particle size and shapes, assuming that the material stays the same. Okay, so after retrieving the refractive indices, then of course we have to do some validation. So that was the second part of the study. So we wanted to reproduce the observed Martian regolith spectrum. And then the third part is retrieval of scattering properties from the measured scattering matrices that Olga showed you before. So we want to model the full scattering matrix measured at 2 different wavelengths, so blue and red light, for L, M, and S size distribution for all of the samples. And then we are just using the derived refractive index together with the scattering database to obtain scattering properties such as single scattering albedo, extinction efficiency, and asymmetric factor. So I will be talking more about the scattering databases later on. And there's a possibility then to fine-tune the retrieved refractive indices as well. Okay, so yeah, this screen is very bad because you cannot see the colors properly. But basically, this was the starting point. So we had first only 2 samples. It's probably easier to look at the other screen that actually has colors. So yeah, first we had the JSC Mars 1 sample and enhanced Mojave Mars simulant MMS2. And yeah, so JSC Mars 1 simulant was glassy, altered volcanic ash from Puunene, Hawaii. Got amorphous palagonite crystallites of plagioclase and magnetites, and it is glassy in texture, whereas the other sample, the MMS2, is quite different. So it has iron-rich basalt mined from the western Mojave Desert. It's got crystalline plagioclase, pyroxene, magnetite, and hematite with trace ilmenite and olivine, and it's crystalline in texture. Now these are the bulk samples received, so these are larger than 200 micrometers in size. And Olga also showed you this before, so the samples went through a very lengthy processing at the Instituto de Cerámica y Vidrio in Madrid. So of course they had to produce the very small narrow size distributions, so they had to mill the sample, and then there was sieving and decantation and centrifugation, and finally we got very nice narrow size distributions. So what we retrieved was then size distributions between 20 to 40 micrometers and size distributions between 63 and 100 micrometers. And then of course we have the bulk sample, but this is what we used, those two smaller size distributions first. And yeah, I think it's better to look at the other screen for the colors. So here we have the JSC Mars 1 with two different size distributions. You can see it has a brownish color. And then we have the MMS2 for the two size distribution with the reddish color. And here we also did some size distribution measurements for. This is the projected area. Yeah, the number density. Or yeah, exactly. Okay. And yeah, the next step was to measure diffuse reflectance spectra for both of the different size distributions for the two samples. Now, this is very interesting because, as I showed you earlier with the clinopyroxene, when you have the same material, but just different particle size distributions, the spectral features should not change. You could only see a difference in the absolute level. Now, this is not what we were seeing after the measurements. We thought that the reason for this was because in the case of clinopyroxene, you have only one mineral. However, these samples, they are a mixture of different minerals. So when you are sieving and producing smaller sizes, then you may select another mineral over another mineral. So there is a different composition there. And there you can see, for example, these spectra are overlapping and they have different features. So there's probably a different composition between these two size distributions, even though there shouldn't be. Now it's very important to look at the colors of the other screens. So in the top panel, we have the large size distributions for both of the samples, and then the bottom panel, we have the small size distributions. And what we noticed is that in the large size distributions, there are these white grains that don't exist in the smaller size distribution. Now, the chemical analysis showed that this is actually quartz in the large size distribution. And this means that the sample is not homogeneous, which is bad for a model because it assumes homogeneous nature of the sample. So we couldn't use at all the larger size distribution, but instead we had to use only the smaller size distribution. Okay, so here are the final samples. So we had to select the 20 to 40 micrometer smaller size distribution in the geometric optics domain. We also added another sample, the MGS1, because it is very different spectrally than the other two samples. So it's good to have as much variety as possible when we are working with the samples. And here we have also the measured size distributions. Okay, so yeah, spectral measurements. So this is the measurements that we did of these samples. So the measurement range was from 200 to 2000 nanometers. and they were carried out at Centro de Instrumentación Científica, University of Granada. Of course, now we have our own spectrometer, so we will be using that from now on. And you can see the spectra are very different. For example, the MMS2 is completely different from the other two samples. So about the modeling part, we know that light scattering computations are sensitive to the particle shapes. And here we have a microscope image of the sample. Well, this is the MMS2 sample. And since previous studies have been using spheres or spheroids or cylinders, we thought it would be nice to try to model with a more complex particle shape that can better describe the complexity of the dust grains. So our first approximation was to use these Gaussian random sphere shapes to model the dust. And here Olga already showed you this, but I'm gonna tell more about this. So this is the modeling scheme that we are using. Basically, what we first do is we are using series 4. This is a ray tracing code. It simulates light scattering by Gaussian random sphere particles that are larger than the wavelength of the incident light. So as I already explained, it's doing ray tracing basically. And what we are doing, we are first computing single scattering properties for individual particle sizes, different particle sizes. And then we are averaging the scattering properties over the measured size distribution that we have. And then the average scattering properties, they are put inside multiple scattering code called RTCP. So this is radiated transfer with coherent backscattering. And we are simulating the surface. So we are looking at the backscattered light. Now this is basically mimicking the experimental setup of the spectrometer. And we first fixed the real part of the refractive index to 1.5. I will talk later about that as well. So the approach was to, try different imaginary part of refractive index until we get the modeled reflectance and the measured reflectance to match. So this is an iteration process. Okay, so here were the first results of the GRS1 particles that we used. So for the uncertainties, we used 15% of maximum uncertainty. This was assumed for the measured reflectance spectrum. We carried out some measurements and came into a conclusion that the maximum error is 15%. And just to be safe, we assumed that over the whole spectral range. So here on the left side are the sample retrieved imaginary part of refractive indices, and on the right are the measured reflectance spectra with the errors. And then when we saw that, we also thought, well, if you're looking at the microscope image, you see that the surface of the particle is not smooth. So there is some wavelength scale surface structure that is not actually taken into account in this model because this is a smooth particle. So we wanted to try different particle shapes to see the effect of the shapes. And we selected spheres because these are very commonly used still. The GRS1 that I already showed to you. Then we wanted to see how the angular particles can also affect the retrieved refractive indices. So we made these polyhedra particles that are just convex particles from the GRS1 particles. Basically, they were created from the GRS1 particles. And then we use this GRS2 particle, which has this kind of a spiky shape. So this actually, previous study has shown that this can mimic the surface roughness of the particles. And here are the results. So we noticed that the derived imaginary part of refractive index, it increases when the particle irregularity increases. So for the GRS2, the spiky particles, it was the highest. And here you can also see I have plotted the GRS1 particles and GRS2 particles together in the same plot. So you see the difference between those two, how the shape actually can affect the retrieved values, and also with the errors. What we also noticed, which was very interesting, was the polyhedra shape. So it didn't really differ from the GRS1 particle. So these angles, they didn't really affect the results. Okay, so as you remember, I assumed real part of refractive index to be 1.5. Now, another good question is it okay to do that? And we did some tests, so we used different values for the real part of the refractive index, and we repeated the optical constant retrieval. And we noticed that actually it doesn't really make a difference. It's within the error limits. So it's okay to use this or assume this 1.5, but only when you are doing this retrieval from a reflectance spectrum. So validation, now a good question is how long our analogs represent Martian dust on Martian surface. So in order to do the validation, we obtained data from the NOMAD UVs. So we got a UV spectrum, and the spectrum, it was selected so that there was a relatively high visible albedo region with limited impact from the atmosphere. So there were no ice clouds, the amount of dust was low, and the solar zenith angle was small, so we were really only looking at the surface. And in this case, in the previous case of the model, so I was looking at the whole reflected or scattered light from the surface. But in this case, we are looking at the scattered light from a certain angle. So the modeling has to be done a bit differently. So this is called the bidirectional reflectance. Since we are looking at the light is coming from a certain angle and only one angle is being measured. So in this case, we again use the derived refractive indices and the series 4 to get the single scattering properties and put them into the multiple scattering code. And this code can also compute scattering from a certain angle. So we use that in our model. Okay, so here are the first results. Again, the colors are a bit bad, but you can see from the other screens. So the blue curve, this is now the actual observed regolith spectrum on Mars. And the other, well, this is the different samples. So the gray one is the MGS1 sample, the red one is the MMS2, and the brown one is the JSC Mars1. And we only tried 20 to 40 micrometer size distribution that we had just to test, just to see how the spectral features look like compared to the observations. And as you can see, the MMS2 is the closest to the observation. So now we took this sample to do tests with, because the other two samples are way too flat spectrally compared to the observations. Now, the next step was to use a proper size distribution for these computations. So previous studies, they have showed that the particle sizes are usually below 100 micrometers in bright regions, but even in the range of 2 to 40 micrometers, so really small. And to better simulate the surface, we used a this is wrong. We actually used a power law size distribution in the range of 2 to 40 micrometers. And we repeated the bidirectional reflectance computations for the MMS2 analog that was the closest to the observed spectrum. And also we used some values in the literature to compare the computations. And here are the results. So I tried different power law indices. Why I used power law on distribution was because we needed a broad size distribution. This was just first approximation, and usually in asteroid studies, they use power law size distribution. Of course, this can be done better, but this is like a whole new study if you want to really study different size distributions. However, the power law size distribution increases exponentially towards the smaller particle size, so it's a good first approximation to see how many small particles there are. So here you can see the black curve again is the observed NOMAD spectrum, and then we have the red one is our modeled values using power law index 1.5, and then the other one is 1.5. Yeah, and then the blue curve, this is the values in the literature, and we used power law index of 3.0. So you can see that with our refractive index values, we can get quite good match. Also, the ones in the literature, this is not bad, but for that you need to use huge amount of small particles on the surface. And as you can see here, the slope is not as steep as with the observation, so there could be some improvements done here for the values. Now, an important question is why are the retrieved imaginary part of refractive index so different from the values in the literature? Now, there can be several explanations to what different particle types, for example, but the effect shouldn't be this large. The problem with observations is you don't really know the particle size distribution either. So you may be using wrong size distributions. Then there is another explanation as well. Maybe the composition of the regolith is different from the lifted dust since we are looking at different size distributions. So could there be some compositional separation? And this is something I want to talk more about because it's better if you look at the other screens again, because this is really important to see the different colors. So this is what happened with the MMS2 samples when the people at the ICV were trying to produce the small particle size distribution. So the first batch didn't actually work out well because it became very light and the color looked very different from the other size distributions of the same sample. So it looked like the composition was completely different or partly different. And so they had to do the process again to retrieve the small particle size distribution, and this time the color was again very different, and this is what we used. But this was more consistent with the rest of the size distributions, the color. But now the good question is, why this happened? So the chemical analysis actually showed that this first retrieved sample, it had a lot of quartz. So it was compositionally quite different. And now question is that, is it possible this is also this kind of compositional separation could operate on Mars as well? Like when you are looking at lifted dust in the atmosphere, this is different composition than the regolith that we see on the surface. Oh, also this is all published, or now it's in press, so you can check it out. Now this is the next part of the study. So now we are looking at the scattering matrix measurements that Olka showed before. So we carried them out in the cosmic dust laboratory. So we are measuring the full scattering matrix there with the two wavelengths, so blue light and red light. And this is the experiment. So we have the sample in the middle. This is coming from an aerosol generator, and we have laser light that then hits the sample. The light is scattered all around. We have a detector. Unfortunately, I don't have it moving here like Olga did, but it is moving around to measure from 3 degrees to 177 degrees. And then we have a monitor. This is important because it's monitoring the sample while we're doing the measurements. So if there's clumps or anything, we can see that instantly. And then the next step for me was, so this is all Olga's work. For me, it was important to retrieve scattering properties from these measurements. So now that we have the particle size distribution measurements, we have the measured scattering matrix elements, we can use the derived complex refractive indices and a scattering database to retrieve scattering properties that are needed then in further models. Now about the scattering databases and scattering properties. So there's really two ways of getting scattering properties. So first one is we can compute the scattering properties from the scratch. So we can use exact methods or geometric optics code, depending on the size of the particles. And we can get the scattering properties. However, since we have different particle size distributions and materials, this is very heavy computationally, as whenever you change one parameter, you have to do the computations again. Luckily, some people have done the computations for us. So there are scattering databases available to everybody where they have pre-calculated scattering properties over a wide range of particle sizes, refractive indices, and wavelengths. So this is what we then chose to do because it's much simpler, is to use actually scattering database to retrieve the scattering properties. So then there are different scattering databases. So how do we select the best one to use? Well, it's very important to try different scattering databases with different particle shapes and try to reproduce the experimental data with the scattering database, and then use the database that produces the best fit with the measured data. Now, in our case, we use two different scattering databases for testing. So we used hexahedra database and triaxial ellipsoid database. So now I want to point out that this is an optical model. So we are not actually trying to see which particle shape resembles the best the sample. No, what we are trying to do is reproduce the scattering pattern of the samples the best we can. And for example, an ensemble of hexahedras can produce the scattering pattern quite well, or even an even triaxial ellipsoids, an ensemble of triaxial ellipsoids, for example. Okay, so this hexahedra database is quite new. It was published in 2021. Then again, this triaxial ellipsoid database, it has been there for 10 years or more. So, I want to talk more about the databases themselves. So if you want to try them out, there's the download link for the triaxial ellipsoid database. So what it contains is the pre-calculated data. So it has 42 different shapes, axis ratios ranging from 1 to 3.3. You have 69 different refractive indices. You can see that the ranges here, and 471 entries for size parameters. In our case, we selected 34 shapes from here because there's lots of spherical shapes, nearly spherical shapes that you can just omit. So why we selected 34 shapes to test was because there's a previous paper by Martikainen et al. Where they were using this database to try to reproduce the scattering pattern of palagonite. And they noticed that these 34 shapes were the best to be used to reproduce the scattering elements. And they also got a quite nice fit using equiprobable shape distribution. So the problem here is that you have so many different shapes, and you have to average the shapes when you are computing the scattering properties. So here is just the way that is done when you're using this database. It's all in their paper as well, so you can check it from there. Now the other database. So here's also a download link to the database itself. So what each data point in the database has is this an example of 20 hexahedral particles. So scattering by this ensemble of these particles. And there are two kernels. So there is a shortwave kernel and long-wave domain. And they have different ranges of refractive indices and size parameters. And then there is the sphericity parameter. So with this sphericity parameter, you can change the irregularity of the particles in the ensemble. So if you are putting it very low, the 0.695 means that they are very, very irregular, the particles within the ensemble. And then again, if you put it high, then these are more regular particles. In general, the authors of the database or the developers, they are recommending to use the smallest value for dust particles because dust particles are very irregular. But you can also play with this parameter. And here they have also the averaging of the scattering properties in their paper. I just put it there to show. In this case, you don't have to worry about averaging the shapes because they do it already within the database when you are retrieving the values. Okay, so the first test that we did was with palagonite because at this point we didn't yet have measurements of the actual samples that are using within the roadmap project. So these were already done before. We had the measurements at the red wavelength, and we wanted to test with spheres, the triaxial ellipsoids, and the hexahedra shapes. The refractive index, we fixed it to 1.6 plus 0.005, according to the best fit solution carried out by Martikainen et al. In their study. And yeah, here is the microscope image of the sample and also the number density, so the size distribution. And here I have the results of the test. So we have the spheres, triaxial ellipsoids, and the hexahedra database that we used. Okay, so the red lines may be better if you look at the other screens. This is quite unclear here. So the red points are, these are the measurements. And then the green curve, this is the ellipsoid database. And then the black one is spheres. and the blue one is hexahedra database. So we are using the same particle sizes, same refractive indices, just different shapes. And as you can see, that the sphere really is not a good approximation at all for the dust particles. It's just you cannot reproduce the measurements. Then again, ellipsoid. Remember, this is a probable shape distribution. You can hone it to be better. It is much better than the sphere. However, when we are using the hexahedra database, we get really nice fits to the measurement. So it's the blue curve. And all of the elements look really nice in this case. So this is why we chose the hexahedra database to use with our samples in the roadmap project. So here I have, I've been taking this as an example, the MMS2, because this was the one that produced, or its spectrum produces the best with the observed spectrum. So I'm using this as an example, but of course I have done all the modeling for all of the samples and size distributions. So first we have the large size distribution measured. And remember, we are now using the hexahedra database together with our refractive indices that were derived before. So there's no free parameters. We have the refractive index, we are using the database, we have the measured size distribution. So we just then put the values in and we get the modeled scattering properties. And again, it's better if you look at the other screen. So here are the measurements at 2 different wavelengths and also the modeling result of 2 different wavelengths in the blue and in the red. And you can see that you can quite nicely model the features here. However, as you can see, for example, in the blue, it looks like it could be done better. Now, this is interesting because what we can do here, we can change the real part of the refractive index since this doesn't affect the reflectance spectrum. And what happens when you are changing the real part of the refractive index is you can get even better fit to the measurements. And yeah, I saw here in this case, in the blue, this is MMS2L, that the 1.6 real part would actually produce a closer fit to the measurements. And what I wanted to test as well was the sphericity parameter. How much do the results change when I'm changing the sphericity? And I noticed, well, it doesn't really change much. So I just decided to stick to the smallest value since it seems to be the closest to the measurements. And here is the medium size distribution. So now we're looking at smaller particles. And unfortunately, we didn't have measurements in the blue for the 3 last scattering matrix elements, but we have for the 3 first. And you can see, for example, phase function can be modeled really nicely with these refractive index values using the measured size distribution. Also, this is not bad either. And the other P22 divided by P11 also looks very nice. Okay, and I did the same test using different real parts of refractive indices. In this case, we are looking at quite small particles, so when you're changing the refractive index, it doesn't really have much difference. So we see similar features. Okay, just to summarize. So we used the advanced light scattering model together with laboratory measurements to retrieve optical constants for 3 Martian dust analogs. And we carried out sensitivity tests, and we saw that the retrieved values are sensitive to the particle shape, but not sensitive to the real part of the refractive index when we are looking at the reflectance spectrum. So the thing is that the selected particle shape, it should reproduce well the measured reflectance spectrum and the scattering matrix. So we tried different databases, and we noticed that the hexahedra database actually produced the best fit with the balagonite, and we used this with our samples. And now we are still working on retrieving the scattering properties. There's more tests to be done. Thank you. Okay.
But not here.
Sorry.
So you know.
Green. It's green? Green? Oh, it works.
Yeah, no.
Okay. So maybe my question is naive, but I ask anyway. So people have been using the spherical shape for the particles for retrievals, and I believe people still use this approximation. So should everyone doing retrieval move to hexahedral particle shapes, or is
Yeah,
the spherical approximation still valid?
no. You should not be using spherical particles at all for effective index retrieval when you're looking at irregular dust particles. This is not right.
So when people retrieve like column dust optical depth with spherical approximations, those I mean, what is the reason for using this approximation?
The reason probably for using the approximation is because it's easy to use. It's more difficult to use irregular dust particles.
But I mean, how much then we believe those retrieved opacities? I mean, is the uncertainty so large now that we should not believe those results anymore?
I think this should be studied, so you should actually use irregular dust particles for that to see the difference.
Thank you.
Is it a microphone? Yeah. Hi, everyone. If you
Just those people here.
okay for the other people. Okay. So if you know the size distribution of your dust cloud and the refractive index, and you compute the single scattering albedo with me theory, the differences are not that strong. The problem is that if you are retrieving the refractive indices by using the me model, then the difference might be very, very strong. And there are many people studying aerosols particles in the Earth atmosphere. So all these sensitivity studies have been done for many years. So you know the errors in the optical depth, single scattering albedo, and so on, based on those studies in the Earth atmosphere. And I would say that not that many people are using the spherical model anymore. What is in fashion in terrestrial aerosols is the shape distribution of spheroids based on Oleg Dubovic's results, but not spheres.
So we've been using these 3-micron MMS2 dust, and we also think that it looks very light. Does this mean that this stuff is wrong or contaminated with quartz somehow?
There could be quartz because it makes it lighter.
So how can that happen if you just mill it and sieve it? I don't see how it get lost in the sieving or.
Maybe it's compositional separation, so you're receiving it. I don't know how that actually happens. You have to ask for those people who have done that. I don't know if Volker knows more.
So this stuff. Okay, so there shouldn't be a problem really. It just seems to be lighter than its reflectance seems to be more than we expected. No, that wasn't us. Wasn't me anyway. Anyway. Okay. Thanks.
Back to the spherical. Thank you. Yeah, I think spherical particles can still be useful. What you look at when you do nadir, when you do a radiative transfer because there are multiple scattering and you need a phase function. There you really need you shouldn't work with spheres. I think when you do occultation and things like that, sphere are still a good. It does a pretty good job, and it's really, as you said, it's really there. People still use it, not when you need the phase function.